Hello everyone, today I'm going to talk about a graph search algorithm, the depth first search. The depth first search, abbreviated as DFS, is one of the most commonly known graph search algorithms along with breadth first search. And in DFS, the objective is to first explore the nodes that are further away from the starting node compared to the immediate neighbors of that node. So today we're going to explore how the algorithm looks. And then we're going to do an example of how the algorithm runs on this example graph with the help of a stack. And then we're going to do a time complexity analysis. So the DFS algorithm starts with initializing the graph, and then we push the starting node to the stack. And after that, while the stack is not empty, so while stack not empty, we pop from the stack, pop current. And then if the current node is not already visited, if current not visited, we mark that node as visited, mark as visited. And then for all the neighbors of that node, for all the edges coming out of that node, we add the neighbors of that node to the stack. We push them to the stack. For all neighbors, push to stack. Okay, so let's do an example. So let's say we are starting from node A in this graph here. So we first push our node, we first push A to the stack. So let's say this is our stack here. So we push A. So the stack is not empty, so we pop from the stack. We popped A from the stack. And then let's say this is our visited node. So we visit A. We mark it as visited. So we popped A, and we push all the neighboring nodes of A to the stack. So B, C, and D are neighbors of A. So we push B, we push C, and we push D. And then we go back to the first step of the while loop. We pop D from the stack and mark it as visited. And then we push neighbors of D to the stack, which is the node E. After that, we pop E from the stack, mark it as visited. And then we push the neighbors of E to the stack, which are F and G. F and G. And then we pop G. G doesn't have any neighbors. We pop F. We pop C. Mark C as visited. So C has D as its neighbor, but D is already visited. So even if we add D to the stack, when we pop it, let's say we pop D, it's already visited. So there's no point in doing that. And then we are left with B. So the order of the nodes that are visited are A, D, E, G, F, C, B. We start with node A, then we go to the first neighbor, one of the immediate neighbors of A, D, and before visiting the other immediate neighbors, we visited the nodes that are further away. We moved on with E, G, and F, and then we came back to the immediate neighbors at the very end steps of the algorithm. So this is how the DFS algorithm works. So let's do a time complexity analysis on this. So initializing the vertices, that is a complexity of OV, if V is the number of total vertices in the graph. And this is because all the initializations are taking O1 time, and there's a total of V nodes, so it is OV. So pushing an element to the stack, it is O1. Checking if the stack is empty, O1, but this is a while loop, O1 with a while loop, we'll go there. Popping an element, O1. Checking if the popped element is already visited, O1. Marking it as visited, O1. And then the tricky part is here. For all the neighbors of the current node, we push a new element to the stack. And the question is, how many times are we doing this operation? So the cool thing about this part here is that no matter how your graph is shaped, the maximum amount you're doing this operation is the number of edges in this graph, because you are never going to visit the same edge twice in this algorithm because you are marking it as visited. This part is important for this. We are marking a node to be visited so that we don't visit that node again for an extra unnecessary time. So the maximum amount of time we are pushing an element to the stack is OE, where E is the number of edges in the graph. So this means that if we include the initialization step to the time complexity of this algorithm, the total time complexity would be OV plus E. This is the time complexity of DFS.